take a look at a couple of important properties of the so-called exponential premium. Rock and roll.
So the first thing we'll do is to define the exponential premium pi of alpha of x as the premium pi of alpha that the insurer is going to charge in exchange for taking on a risk of size x. Now, the alpha is just a parameter, which, for instance, in the case of Lundberg's model, stands for the so-called adjustment coefficient. Now, what we do is that we multiply 1 over alpha times the natural logarithm of the moment generating function of the risk x evaluated precisely at alpha. Now, the first property we will be reviewing today is that when alpha tends to 0, then the exponential premium tends to the so-called net premium, the expectation of x, as alpha tends to 0. So we could be tempted to do something like just take the limit when alpha tends to 0 of the natural logarithm of x evaluated at alpha divided by alpha. However, this would lead us to an expression of this form, which is just nonsense. So in order to solve this conundrum, what we'll do is to take a look at L'Hopital's rule approach to solving the problem. To do that, what we need is just to take the derivative with respect to alpha of the numerator and then evaluate it at alpha equal to 0. And of course, also to take the derivative with respect to alpha of the denominator of the same expression and also evaluate it at 0. Now, it is very straightforward that this part here equals just a 1 because the derivative with respect to alpha of alpha is just a 1, and we no longer need to take this evaluation. However, for the case of the other part here, what we need is to recall that the moment generating function of a risk of size x is just the expectation of this exponential right here, and then of course evaluate it at 0. So what we need is just to take the derivative with respect to alpha, which is just the derivative of this part divided by this part again. So what is the derivative of the expectation of the exponential of alpha times x? Well, that is just the expectation of x times the exponential of alpha x divided by the expectation of the exponential of alpha times x. And when we evaluate this expression at 0, what we have is that these exponentials just tend to 1, and we are left with the expectation of x. Now, if we divide this expectation by this number here, what we get is precisely what we wanted. The second property we'll study today is the one that says that the exponential premium is an increasing function of alpha. Now, to this end, one would of course try to take the derivative of this exponential premium and see that it is a positive number. However, when we take this derivative, what we get is just something like this. Now, I don't know about you guys, but at least to me, it is not clear at all that this thing here is actually a positive number. Can you see that? I mean, what we need to compare this number here with this other number here. So it is not clear at all. However, what we can do is rather than taking this derivative here, we can first try to prove this result, this theorem. The derivative with respect to alpha of alpha squared times the derivative with respect to alpha of x equals alpha times the variance of the so-called Escher transform of the random variable x, where this x of alpha is a random variable whose density function is given by the exponential of alpha times x times the density function of the random variable x evaluated at x divided by the moment generating function of x evaluated at alpha. Now, should we prove that this result holds, then to see that the derivative of the exponential premium is a positive number, the only thing we have to do is to take what? The integrals here. Because the integral of this differential just gets cancelled. And then what we'll have here is just that this expression here, which is just of a positive number times a number which we want to see that it's positive indeed, equals the integral of a positive number times another positive number. So there is no way that this expression here is negative. So as you can see, is that we're going to prove that should this hold, then the integrals will give us what we want. Now, what is the derivative with respect to alpha of alpha squared, the derivative of the exponential premium? Well, this derivative is just something like this. And then we can just cancel these two factors here so that we just end up needing to calculate the derivative of this expression here. But it is not difficult to see that this thing here equals alpha times the derivative with respect to alpha of the expectation of x times the exponential of alpha x divided by this plus the expectation of x times the exponential like this divided by this moment generating function minus, right, the expectation of this expression here. And now please note that in here we have just two terms with opposite signs, so we can just cancel these two out. So we just need to compute this derivative. But we can just use the quotient rule to see that we just need to write the moment generating function of x times this expectation minus the expectation of x like this square divided by this moment generating function square. Now this is just alpha times the expectation of x squared times the exponential of alpha x divided by the moment generating function of alpha. Then we could just subtract the expectation of x like this divided by the moment generating function of x, all that to the power of 2. And just observe that in here what we have is just what we needed to have, which is the variance of the Escher transform of the random variable x. So what we have is that the derivative with respect to alpha of alpha squared times the first derivative of the exponential premium equals alpha times the variance of the Escher transform of the original risk. Now, as we said before, we can just complete our proof by taking integrals and see what we were seeing before. That is, these two cancel each other out, and we're left with a positive number, which proves what we wanted to prove. That is, that pi prime is a positive number. Hence, the exponential premium is an increasing function of alpha. That's it. Thank you very much for your attention. Until next time.